believe it or not, at least the first half of what we're going to talk about today is going to seem overly easy. But I think that's a good thing, and hopefully you take this message away from our discussion today on the math part of the class, that the calculus involved in thermo is relatively straightforward. In fact, all of the calculations I feel are relatively straightforward, where you're either doing algebra or you're doing very basic integrals and derivatives. And so if you're comfortable with what we do today from a math perspective, you will be fine for the rest of the semester. And one of the things I really like about now hosting these videos on YouTube is that you will do these integrals multiple times over the course of the semester. And you'll have a resource that you can go back and pretty easily look at what we've been doing. So the first integral I want to do is extremely simple, right? So we're just going to take the integral from x1 to x2 of x dx, right? And I won't bother you guys with, chiming in, right? That is simply 1/2 x squared evaluated from x1 to x2, which of course is just equal to 1/2 of x2 squared minus x1 squared. And I use this as the first example because one of the most common integrals that we're going to take today or during the course of our class are things like calculating the enthalpy. And so in a real example, we could say, all right, well, let's find, delta H, to heat a gas from T1 to T2. Well, at the beginning of our semester, we're going to be able to assume that the heat capacity is constant, but later we'll learn even for ideal gases that this isn't the case because of the different modes by which substances store energy, whether it's translational movement, whether it's rotation, vibration, and those don't all scale perfectly linearly with temperature. And so what you find is that when gases store energy, they tend to deviate from linearity as you go to higher and higher temperatures. And so you get these equations that are really empirical fits, just like the Antoine equation is, where the heat capacity is equal to, A plus BT plus CT squared plus, DT cubed. So that's the equation that's used in the back of your book. And of course, in 300, you guys already calculated delta H, right? And you said that delta H was equal to the integral from T1 to T2 of Cp dt. So a very common integral then that you'll end up taking in this class is that now we're going to integrate from T1 to T2 things like A plus BT plus CT squared plus DT cubed, right? DT. And even this heat capacity we're going to use later on in the semester when we talk about entropy. You'll even see that a little bit in our lecture today. So of course, if we're going to evaluate this integral, well, we know then that the solution to this really is just A times T plus 1/2 BT squared plus 1/3 CT cubed plus, oops, I said 1/3, I wrote 1/2, plus 1/4 dt to the fourth evaluated from T1 to T2, right? So you would find then that delta H to heat a gas from T1 to T2 using that equation for the heat capacity is just A times T2 minus T1 plus B over 2 times T2 squared minus T1 squared plus C over 3 times T2 cubed minus T1 cubed plus D over 4 times T2 to the fourth minus T1 to the fourth, right? And that's a very simple but common application of just taking the integral of a polynomial. Another really common integral that we're going to take in our class, in fact, you'll take this integral in your homework this week, is the integral from x1 to x2 of 1 over x dx. And of course, that is the natural log of x evaluated from x1 to x2, which is just equal to the natural log of x2 over x1. Another common integral is the integral from x1 to x2 of 1 over x squared dx. And of course, that is minus 1 over x evaluated from x1 to x2, right? Which is just equal to minus 1 over x2 minus a negative 1 over x1, which equals 1 over x1 minus 1 over x2. And I know it might sound almost unbelievable, but if you can do all of those integrals, you should be okay, at least from an integration perspective throughout the semester, okay? So before I move on to some discussion on derivatives, is this okay? Is everybody comfortable with this?
Yes.
All right, good. Hopefully for you guys, this feels like some sort of rudimentary review. So that's what I was hoping for, and hopefully that builds some confidence. All right. So now we can do a couple of really simple derivatives at the beginning. And I'm not kidding that if you know how to take, d over dx of x squared, right? Well, that's of course just equal to 2x. And you're able to take d over dx of 1 over x, right? Which is 1 minus 1 over x squared. You're going to be fine. The more complicated concept here is actually not in taking the derivatives. I think what we want to be able to do during the semester is to understand conceptually what a derivative is asking, and we're going to use that to our advantage. So I'm going to pick on this second derivative a little bit, and I'm just going to multiply both sides by dx, right? And this says d 1 over x equals minus 1 over x squared times dx, okay? And really what that derivative is asking us is, how does a function change with variable x, right? And that function is, 1 over x change with variable x, right? And we could ask that question with any generic function, right? So we could say that, you have the derivative of some function is equal to, how it changes, right? Which is the derivative with respect to some variable x, right? And of course, that's just equivalent to df dx, right? But I want to use this idea, which might seem silly to you guys, with one independent variable and one function, or one independent variable in the function, right? These appear to be equivalent, but asking this question of how does a function change with a variable, and really thinking about it from a differential perspective, has much more utility when you do this with two or more variables. And that's where we're getting into the multivariable calculus part of our discussion today. And of course, if you haven't taken that yet, hopefully this is like the first lecture in multivariable calculus or something very close to it. But the question that we're really going to ask ourselves is, how does some function change with two or more variables? And maybe we can illustrate this with an actual example. So let's say, how would a function f equal to ax squared times y cubed change as a function of x and y? Or maybe change as x and y are changed. That might be a better way to do this. So if we use maybe the previous example as a template, well, the total change of our function, remember, was just df, right? So we know that that's the change in f. And now we have to find a way to express that relative to changes in x and changes in y. So we know at some point here, we have to have the rate of change of x, or dx, and we have to have the rate of change of y, or dy, inside of the right-hand side of our equation. And the way that you do this, and you take the total derivative of this function f, is that you can consider how they each change independently of one another. So we can say that df is actually equal to something called the partial derivative of f with respect to x at constant y, and that's what that little subscript at the bottom means, plus the partial derivative with respect to y of that function at constant x. And this thing, for those of you who haven't taken multivariable calculus yet, this partial derivative essentially means that we're going to pretend in our function that we're just taking the derivative with respect to this variable of interest and assume that everything else inside of that function is equal to a constant. And so I want to do that here, right? So let's find df dx at constant y. So we know, right, our function is ax squared. Oop, that's a terrible squared. Ax squared times y cubed, okay? Now, if we're going to pretend to take this partial derivative that y is equal to a constant, right? So we have df dx at constant y, then equals df dx, or sorry, d dx x of ax squared times y cubed at constant y. And the really nice thing about this is that if y were constant, that means that we just have to, that we can take it outside of that derivative. So that becomes a times y cubed times d over dx of x squared, which of course is 2 times x. So then we know that df dx at constant y is then 2 times a times x times y cubed, right? Because y was equal to a constant when we took that derivative. So now let's do the same thing for that function, right? Let's find df dy at constant x. So df dy at constant x then equals d over dy of ax squared times y cubed at constant x. And we're going to be able to do the exact same thing here because x now is equal to a constant, and of course so is a. So we have ax squared times d over dy of y cubed, which is of course 3 times y squared. So that derivative, df dy at constant x, is 3 times ax squared times y squared. And if we combine those two, we actually have the total derivative for f. So we know that our function changes with respect to x and y by 2axy cubed dx plus 3ax squared y squared times dy. And we have a function now that describes, or we have an equation now that describes how our function is going to change as we change x and y by some amount, right? Some delta x or some delta y. We could actually find the change in F. So hopefully that makes some kind of sense, and at least the math makes sense. And if not, please come back and revisit. Feel free to ask questions, right? We have office hours today. That would be a really good time actually to talk about either this or of course the homework problems, which is mostly what we'll probably do. But I did this math because we're going to use it to ask something that feels like a much more fuzzy but practical question. So let's ask one, and we'll apply the same math, but to variables that mean something to us. So let's ask a question like, how does entropy, which we'll talk about a lot in our class, change as a function of temperature and pressure? Okay, so the previous example might mathematically make some sense, but the application to class isn't exactly evident. But let's do the same thing that we did in the previous problem, right? Where remember, we had a function f, and we had so we had some function f which changed with two variables, right? X and y. In this example, the function that we're interested in is the entropy, right? So we know that the entropy then is a function of temperature and pressure. So if you look for equivalence in our previous problem, right, we're going to say S is kind of the same as F was, T is kind of the same as X was, and pressure is kind of the same as Y was in that previous problem. So if we apply that same math, remember we got to this place where df was equal to df dx at constant y, dx plus df dy at constant x dy. So we're going to do the same thing here. And if we apply that, now we have this change in the entropy, which is ds, is then equal to, if we convert x to t and y to p, we have dt dp. And then we have a very similar kind of derivative. So we have now ds dt at constant p plus ds dp at constant t. Interestingly, we know, believe it or not, what those are. You might not know yet, and we'll derive these as we move through the semester. But it turns out that the definition for the constant pressure, right, because this is constant pressure, the definition for the constant pressure heat capacity is actually T times ds dt at constant P. That's the mathematical definition, which means that this term here is just Cp divided by T. And hopefully you guys have some feeling for what the heat capacity is, right? Or at least you are used to using it. And this term here, ds dp at constant T, we'll derive this later in the semester. It turns out that's just the ideal, for an ideal gas, that's the ideal gas constant divided by the pressure. And so now we actually have an equation that we'll use later this semester, that the change in the entropy is equal to Cp over T dt plus R over P dP. And we're going to have examples where we're going to be asked to find the change in the entropy when the temperature goes from this to this and the pressure goes from this to that. And we'll also have examples during the course of our semester that ask things like, you have a process that is adiabatic, right? Which means that it doesn't exchange heat with the system doesn't exchange heat with the surroundings, and reversible. And we'll talk about what that means later. And that means actually that ds is equal to 0. And so now what we'll have is initial conditions and a final condition. We'll have to find either one of the temperatures or one of the pressures. And so we'll end up using this equation in a bunch of ways, but it's built from the same math that we did up here, right? And if you've had, hopefully if you've had multivariable calculus, that makes some kind of sense. And if not, don't worry. This is as much of multivariable calculus as we're going to use in our class this semester. So as long as we can get to here and we can take a couple of integrals from here, you should be fine. The other thing that maybe is interesting is you could ask the exact same question about enthalpy, right? So you can ask, you know, how does enthalpy change with temperature and pressure, right? Because you're used to finding at least the enthalpy of formation at standard conditions, right? And you would do the exact same thing that we just did above. And now our function is h. And so delta h, or dh, sorry, not delta h, would be the partial with respect to temperature at constant pressure dt plus dh dp at constant t dp. And we know actually that this is the heat capacity. And actually you should know that because you know that this equation is going to end up simplifying to dH just equals Cp dt. At least it does for an ideal gas, because one of the things we'll derive later on in this semester is that dH dP at constant T is actually equal to 0 for an ideal gas. And where we end up, right, is that dH equals Cp dt. And in fact, you know, I chose to define the heat capacity this way. Some people actually start by defining the heat capacity from here. And they're actually mathematically equivalent, but we won't show any of that. So if I just take a second to summarize what we did so far, right, today, and trying not to give you guys whiplash. From an integration perspective, our class, quite frankly, is very straightforward. That if you can do polynomial integration, if you can do 1 over x and 1 over x squared, that's pretty much all the integration that you have to know how to do in thermo. For taking derivatives, you know, taking derivatives of certain functions is relatively easy. The one thing to maybe try to wrap your head around when you go back and either look at the video later or look at your notes later is trying to understand a little bit better what a derivative really is and how it's really describing the rate of change of a function with respect to x and y. And maybe they said that the first day of calculus and they, you know, drew a curve and said, oh, the rate of change is the tangent at some point here. Okay, that's fine. But when you take a calculus class or just a math class, you know, lines on curves, I think, don't mean as much as when we get into real applications, like when we're talking about thermo. Now we can ask real questions just using the math that they did. That, okay, how does some variable that we really will care about later, or some variable that we're really going to care about very soon, change with things that we can actually measure?